Hey, welcome back to Graph Theory. In this lecture, we're going to move into the second section of Chapter 9 and talk about some problems related to colorings in planar graphs. All right, so you can see the outline there in front of you. What we're going to do, we're going to kind of introduce and motivate the whole thing with an old problem about coloring maps. And then we'll convert that map coloring problem into a vertex coloring problem of a graph, a planar graph. Then we'll just discuss, not prove, but discuss the most famous theorem in all of this business, the so-called four-color theorem. Probably heard of it before because it's one of those theorems that's easy for people to digest, and it kind of intrigues the human imagination. And then we're going to give a proof due to Hewood of these, I'm sort of sarcastically saying, slightly less famous five-color theorem. Of course, the five-color theorem follows from the four-color theorem, but the four-color theorem was much more difficult to prove. Okay, so let's get into it. Let's start by looking at the history of the problem. The origins of the four-color problem, of the story goes, trace back to the 1850s when an English mathematics student called Guthrie, Francis Guthrie, noticed that he could color the counties in a map of England using only four colors in such a way that no two counties that shared a border would be the same color. All right, I'm showing you a map of the U.S. and for purposes of this, sorry, Alaska and Hawaii, I'm going to kind of be ignoring those non-contiguous parts, contiguous meaning all in one piece. But here's a four coloring of the map of the U.S. All right, so you can see that if you pick any two states, like let me test my geography here, Oklahoma and Texas, they share a border, they can't get the same color. Any two states that share a border can't get the same color. Notice the four corner states here, Utah, Arizona, New Mexico, and Colorado, have a vertex in common. For purposes of this business, we wouldn't consider that a shared border, okay? So in this map, Utah shares a border with Colorado, but it doesn't share a border with New Mexico by the definition that we're giving. So when I say two countries, states, counties, whatever you like, when I say they share a border, I mean they actually have some length that they share it along. It has to be more than just a point. Okay, so Utah, it borders Arizona. I'll test my geography again. Nevada, Idaho, Wyoming, and Colorado. That's it. Utah does not border New Mexico in this definition. I apologize to any citizens of Utah or New Mexico who wants to quibble with that. So it shows a four coloring of the US. So I'm talking about these restrictions on our map. What are our restrictions? Well, you have to have contiguous countries. You can't have nations that have sort of an island state out somewhere. So they have to come in one piece. Here, let me show you a map. I'm just kind of crediting where I got these images, both from Wikipedia in those URLs there, hopefully not violating anybody's copyright. I'm not making any money off of this. I'm telling you my sources, so I think I'm okay. So the countries have to be contiguous, all in one piece. Like in a map like this, if we're insisting that a country get a certain color, if country A here has two pieces, then this map would require five colors, because country A is in two pieces, and those two pieces together are bordering four other countries that are all bordering each other. And so you couldn't four color such a map. So when we talk about maps, we're excluding such possibilities, all right? So think about the map of, I don't know, the US, the contiguous US, or here I think I have a new graphic taken where I want to convert this thing into a graph theory problem. Maybe we can talk about some counties that we care about up here in the far north of California. For purposes of this, I should have just cropped the picture, but we won't. I'm not going to fill in the whole thing. But here you're looking at a map of some counties in Northern California. It's not four colored, I don't believe. It looks to me like they have used more than four colors to color this map. So they had some other thing in mind. Yeah, I actually kind of think, I hope this isn't annoying to scroll too much on you here, but four colored maps actually kind of tend to look a little boring. So you don't really see a lot of these things in practice. The color schemes can kind of be more enriched. So I don't know exactly what the color scheme on this Northern California tourism site that I took this map from was, but here it is. But let me tell you how you can take any such map, an admissible map, I'm going to be calling them, and turn them into a planar graph as follows. You select a point in each one of your, here it's counties, countries. It's kind of convenient. Why don't we select the points to be the county seats, the county capitals? So Humboldt County will select Eureka, Crescent City and Del Norte, Wairika up in Siskiyou, Weaverville in Trinity County, so on. So you pick the county seat to represent each one of your countries, your regions, your counties, okay? And then you draw an edge. So those are the vertices in this graph. The vertices in the graph are the county capitals that you pick. And then you draw an edge between two counties here, countries, or whatever you want to call them, if those two things share a boundary. So Del Norte County boundaries Siskiyou County and more than a point, so I connect those. All right. Humboldt borders Del Norte, so I connect them. Humboldt borders Trinity, we connect them. Trinity borders Siskiyou. Border. So you get the idea. Over here, Susanville has to get connected to Alturas. So does Wairika. So does Redding. Because look, Shasta County has a non-point border. All right, Redding. Let's ignore, pardon me, Mendocino, Tehama, Glenn County, Butte County, Plumas County. Let's just say that we're looking sort of north of, how do they say it in the movies, this thin red line. All right, so if we're only considering counties that are north of that line, then I've completed this planar graph. All right, so that's how I take a map, an admissible map by our definition, and I convert it into a planar graph. And then a coloring of this map just corresponds to a vertex coloring of our graph, because two countries or counties are going to be adjacent if and only if the edge is between the corresponding vertices. That's how we defined this graph. All right, so we've just converted our problem into an old graph theory problem. We're asking for the chromatic number of a planar graph. What's the fewest number of colors necessary to color the vertices of a planar graph according to our vertex coloring scheme? All right, so it's a famous theorem. Its origins were born in the 1850s with this Francis Guthrie, who you can read in your book. I guess his brother was a student of a famous mathematician, De Morgan. Maybe you've heard of De Morgan's laws. And that's really how this kind of problem weeded its way into the mathematical circles, is that De Morgan thought it was kind of interesting and couldn't prove it. So it kind of started making its way around. All right, it was 120 years later, or closer to 130 years later, maybe. I don't know when in the 1850s Guthrie posed this, but three mathematicians, Appel and Hankenwell, and a computer scientist, Cook, finally gave a proof of the so-called four-color theorem. I should write it here. It's theorem 9.6 in your book, but people call this the four-color theorem. The four-color theorem says that if G is a planar graph, then its chromatic number is less than or equal to 4. All right. The proof of this theorem, I certainly have never read it or tried to digest it. It's very complicated in its entirety. It was published first, I think, in 1976, but then had to be corrected several times. And it's in entirety, it's more than a 700 long page proof that has many, many technical arguments. There are these notions of something called unavoidable configurations. And basically, I think the nuts and bolts of the proof, the 10,000-foot outline of the proof, is that they gave a mathematical argument that there was a sort of finite and known list of these unavoidable configurations in a planar graph. And then they exhaustively, via computer search, checked every single case, every one of the graphs of what these unavoidable configurations in it, and could four-color them. So it's sort of a computer-assisted proof in the sense that a human mind says that, well, except for the very large number of exceptions, we can do this. And then the computer looked at each one of the exceptions one at a time and said, we can always do it. Some mathematicians, I'm not one of them, think this is some kind of controversial proof because it involved checking a large number of special cases via computer. Some people want some sort of, I don't know, closer to, I don't know what they expect. To me, it's a proof. If they've mathematically proved that, any planar graph has to have these certain number of things, there's a mathematical proof that that list is complete, not missing anything. And then so what? You have a computer check all the cases because it's large. In my opinion, it's a proof, but I'm just an algebraist trying to make a living here. All right, so what are we going to do in this lecture? I can walk you through an argument that was much earlier, just 30 or so years after Guthrie posed the problem due to Heawood, that every planar graph is 5-colorable. All right, so this is the less famous, I'm not sure if really people even call it this, but I'm going to call it the 5-color theorem. Okay, certainly the 5-color theorem follows from the 4-color theorem, but that's not going to be our proof. We're going to try to give the proof that Heawood gave. Heawood couldn't cite the 4-color theorem because it hadn't been proved yet for another 90 years. Okay, so we're going to proceed by induction. We're going to proceed by induction on the order of G. Okay, and the base cases, well, you can take just one of them if you want, but the theorem is clearly true if the graph has order less than or equal to 5. Yeah, if you give me a planar graph that has no more than 5 vertices and I can't 5-color it, then I have a big problem. So the induction hypothesis is going to be then that for some n that's at least 5, that all planar graphs of order n are 5-colorable. Okay, so that's my induction hypothesis. It's something I'm assuming, and then what I have to start with. Some of you guys are still learning how to write induction proofs, so I'm kind of trying to emphasize my proof needs to start by saying, give me some planar graph of order n plus 1. I can't build it from a graph of order n or anything like that. It has to be handed to me. I walk out on the street and I say, somebody, give me a planar graph of order n plus 1, and somebody hands it to me. I don't get to say anything special about it. I just know that it's planar and it has order n plus 1, and my job is to convince you that it's 5-colorable. Okay, I'm going to use similar notation to in our counting arguments in the previous section, that the Q denotes the size of this graph. So I'm going to start off. I could just cite a corollary from section 1, but I didn't prove it. So let me prove it here. That if in this planar graph, if the minimum vertex degree, that's what delta G means. If that minimum vertex degree was at least 6, so every vertex in this graph has degree at least 6. Well, then remember our very first result in this course. The sum of the vertex degrees is twice the size. So if every vertex has degree at least 6, then twice the size would be at least 6 times the number of vertices. And then a little bit of algebra, that would mean that Q is greater than or equal to 3n, which is certainly strictly greater than 3n minus 6. But theorem 9.3, which we did prove, theorem 9.3 says that the size of a planar graph is less than or equal to this number. Okay? So we have some planar graph. It cannot be the case that its minimum vertex degree is at least 6. Delta of G has to be less than or equal to 5. This is your author's corollary. I don't know, 9.3 something. Okay, so in our planar graph, we have to have minimum degree at least 5, or sorry, less than or equal to 5. So let's pick a vertex of minimum degree. Okay, so choose a vertex V in your graph. Its degree is delta of G. The graph has to have such a vertex. So I pick V, its degree is less than or equal to 5. Okay, so now we're going to get into the induction. Take that vertex out of the graph. That gives you a graph of order n, and removing a vertex, it's going to kill some edges too, but it's not going to make anything unplanar, right? So I've got a graph of order n. G minus V is order n. So the induction hypothesis says I can 5-color that graph. Okay, so for some notation later on in the proof, let's call the colors C1 through 5. And I've got a 5-coloring of this graph, G minus V. Okay, so now I'm just going to kind of walk through a bunch of cases. It seems that the proofs in graph theory are always weighted down in lots of cases. So maybe I luck out and the degree of this vertex V is actually no more than 4. I don't know what the degree is. I know it's no more than 5. Maybe it's actually no more than 4. Well, then the neighborhood of V can't contain all 5 colors. There has to be some color Ci that's not present in the neighborhood of V if V only has 4 at most neighbors. So then just give V the missing color and you 5-colored your graph G. Right? There's a color available for V in this case. That's all I'm saying. So we have to tackle the tougher case that there's no color available for V. We have to change something. We're going to have to change this graph coloring somehow because we're looking at the case where the degree of V is 5. Okay, well, maybe we don't have to change something. It still might be possible, even if V has degree 5, that the neighborhood of V doesn't use all the colors. If there's a color CI that's not in the neighborhood, same thing I just said above. Give V color CI and go home. We're done. Okay. So what case are we in? The actual case. I'm kind of drawing a picture to show it. I've got a neighborhood of V. It's got 5 vertices in it. Call them X1, X2, X3, X4, and X5. And for convenience, well, in the case I'm in this neighborhood of V has all 5 colors. And let's just for convenience say that vertex Xi has color Ci, so we don't drive ourselves crazy, okay? So X1 is colored C1, X2 is colored C2, and so on. They're all 5 there. So I can't do this kind of easy give V the color that's missing because nothing's missing. Cool. So getting a little technical here. For every pair of indices, I and j between 1 and 5, but I is not j, I'm going to denote by gij the induced subgraph of G that uses all the vertices that are colored Ci or Cj. Okay, so let's say that I'm picking like color red and blue. So all I'm doing is saying, look in the graph G and find all the vertices that are either red or blue, and then just take those vertices together with any adjacencies between them that were in G. That's what I mean by the induced subgraph, okay? It may or may not be a connected graph. It might split G up into a whole bunch of pieces. I don't know if it's connected or not, okay? Let's notice that by definition, the vertices x1 and x3 would be in the vertex set of G13 because x1 has color 1 and x3 has color 3, okay? So we're gonna look at two cases. We're getting there. The first case is that x1 and x3 are in distinct components in this graph. It's a disconnected graph and x1 and x3 are in different components. So in the component that contains x1, every vertex in there is color 1 or 3. Or sorry, oops, typo. Change that into a 3. So in the component containing x1, every vertex in there is color 1 or 3 because I'm in G13. So what I do is just swap them in that component only. Take the vertices that were color 1 and make them color 3 and vice versa. Okay? It's not doing anything to any vertices outside of this component. It's just interchanging the colors in there. And I claim that doesn't ruin the coloring of G. Because how could it? Well, no vertex in G that's adjacent to something in this component has either one of these two colors, right? No vertex in G that is adjacent to one of these things has color C1 or C3 because otherwise that vertex would have been in this component. It would have been in G13 and in this component. So no vertex outside of G13 that's connected to one of anything in this component has these two colors. So we're not ruining that. And then the vertices outside this component, in other components that do have vertex C1 and C3, they're not adjacent to anything in here because otherwise they would have been in this component. All right? So we didn't ruin the coloring. Stop the video, think about it, but swapping the colors C1 and C3 in the component that contains X1 gives a new coloring of G, but it's still a coloring. Okay, well now up in our little picture, I've got another copy of it down here, but X1 now got color C3 and X3 still does. So sorry, I am gonna scroll. So what we've done is now these two things that originally had colors C1 and C3 now both have color C3, okay? In the other vertices in the neighborhood, we've got 2, 4, and 5. So color 1 is available for V, and that's what we do. We give V color 1, and we have 5 colored our graph, okay? So we give V color C1, we're done. Okay, last case. It's the complement of our case above, that X1 and X3 are actually in the same component of G13. It's possible. Well, if they're in the same component of G13, then there's a path in G13 between them. So I'm just going to call that path P13. Everything I'm saying has a 1,3 after it, so I might as well call this path P13. I've drawn it over here. I don't know what it looks like. I don't know how many edges there are, but every edge in it has a vertex that's colored 1 and 3. Color 1 or color 3 because it's in this subgraph, and it's a path between those things. Okay, I drew it right there. Of course, you could draw it other places, but it has to start at x1 and it has to end at x3. I know it doesn't go through x2, x5, or x4 because those don't have color 1 and 3. Those have colors 2, 4, and 5. All right, good. So complete that path. Make it a cycle. I'm calling the cycle C here if you've already read it, by just throw in the edge x3v and the edge vx1. All right, that makes a cycle in the graph G13. Yeah, and x2 and x4 by construction are on opposite sides of that cycle, sides in the sense of the Jordan curve theorem. So any path in G24, now you're kind of starting to see why I picked 1 and 3. In the above part of the proof, they didn't have to be, but any path in G24 from x2 to x4 by the Jordan curve theorem has to cross our cycle C. But G is a planar graph, so paths cross only at vertices, right? G is planar, so paths cross only at vertices. But on C, all the vertices are color 1 or 2. And any path in G24, all the vertices would be color 2 or color 4. So at the vertex where this path crosses C, we have a problem because that vertex has to be either color 1 or color 2 because it's on C, but it has to be either color 2 or color 4 because it's on this path. Well, it can't be both. So there is no such path. Yeah, there can be no path in G24 from x2 to x4. There can't be one. Well, what does that mean? That means in the graph G24, x2 and x4 are in distinct components. So just go back to the argument that we gave in case 1, but apply it to x2 and x4. Take the component containing x2, swap colors C2 and C4, come back to the graph and give vertex V color C2, and you're done. All right, so that is Heawood's proof of the 5-color theorem. Thanks for listening.